All right, we're just finishing up the second side of the Chapter 3 review. Number 11 wants you to determine whether the function is continuous or discontinuous. There are three forms of discontinuity. Point discontinuity, which is where you have a line and it's going along and then you have a hole there. Jump is where you have a line or some kind of curve and it stops and then starts at another point and continues. And then infinite discontinuity is when you have an equation or a graph of an equation where you'll have asymptotes, and so it never you never cross that asymptote. It changes infinitely there. I'm going to do 11 and 12 on Desmos. We'll see how that works out. So for number 11. Let's try this again. Number 11, we have x squared plus 1. We have the graph of that. We only want to keep the portion where its x is less than 1. So we're going to have an open dot at 1 and only keeping that portion of the graph. I'm going to hide that for a moment. Then I'm going to add a second one. That second half for number 11 is negative x cubed. Plus 2. This time for this graph, I want to use where x is greater than or equal to 1. So I find greater than or equal to, I'm going to have a solid dot there, and then everything that's greater than 1 for x. When I hide that, you can see that there is a disconnect between the two portions of the graph. This is jump discontinuity, and that's because we have this space in between and then it picks up at point 1 again. Now there is a value at 1 where x equals 1, there is a point. It's filled in, so I would say it's continuous there, but the type of graph has joint or jump discontinuity. Right, then I want to look at number 12. Number 12 is x squared plus 9 over x plus 3. And we look at that graph. You actually have to zoom out a little bit to see the whole thing. For this one, it's not point discontinuity, it is discontinuous, but it's not jump discontinuity either. This one, because we do have an asymptote, the asymptote is the vertical asymptote where x plus 3 would equal 0, so x equals negative 3 would be the asymptote. So this is infinite discontinuity. And because x equals negative 3 is an asymptote, that means there's no points where the graph goes through that, so it's discontinuous at that point. So this is number 13. Number 13, it asks us to describe the end behavior. Again, let's graph it. Let's take a look at the ends of the graph and see what it looks like. So we have y equals negative 3x to the 4th minus 2x. There's the graph of the equation. I'm going to zoom in a little bit so we can see it a little better. It looks like that's it. The end behavior, what's happening to it here is our graph is going in this direction. So on the left side, as x approaches negative infinity, so going to the left, we say y approaches negative infinity. And on the right side of the graph, as x goes to the right, so it's approaching positive infinity, y is also, again, approaching negative infinity. So that's the end behavior for number 13. Okay, 14. Let's graph it again. We want to locate and classify the extrema of the graph. That's like our maximums and minimums. Y equals x to the fourth minus 3x squared plus 2. So we actually have 2 points of, we have an extrema here, here, and here. If you look at the coordinates, clear those out real quick. We have a maximum at 0, 2. But it's not the highest point. So this is called the relative max. And it's at 0.02. And then we have 2 minimum points. They both go down the same amount. So this is actually an absolute minimum. And since they go the same amount and they're the lowest points, I'm going to go ahead and list them both. Sometimes you can list that the minimum is at negative 0.25, but we can list the ordered pairs here. We have negative 1.225, actually plus or minus, because there's 2 of them, we can do it all at once. And the y coordinate is negative 0.25. Since it's wanting the location, we should really give the ordered pairs of those. So we have relative maximum, and then we have absolute minimum. We actually have 2 because they both go down the same distance. Number 15, it's asking about critical points. Critical points are your max, min, and also any points of inflection. So that inflection just means where it changes. Our graph is y equals negative 3x squared, or excuse me, x cubed, minus 3x squared plus 3x. So there's our graph. It wants to know if we have a maximum or minimum value. I'm just going to zoom out just a little bit here and really check the graph, and it looks like it's all just this one. I don't see that we actually have a maximum or minimum point. It has to be like the top of the hill or a valley. But I do see that we have what looks like a point of inflection, and that's where it's going to change directions. It looks like at about 1, 1 is where it's going to change directions. I don't going to let me keep that. It's not necessarily a high point or a low point, but it's just where the graph changes direction. It says it has a critical point when x equals 1, and like we said, it's a point of inflection at 1, 1. Number 16, we want to determine the vertical and horizontal asymptotes for the graph of the given equation. What I'm going to do do, I'm just gonna write the equation down here for a minute, we can look at it in just a second graphically, but this is number 16. We have x squared minus 4 on the numerator, and x cubed minus 5x squared plus 6x in the denominator. The first thing we're going to look at is for a vertical asymptote. And that's going to be where the denominator equals 0. So that's what we want to look at. And then to find out when x equals 0, we have to solve. We actually have to do a little factoring here. We have an x in each term, so I'm going to take out a common monomial of x. And then I'm also going to see if I can factor this trinomial a little bit. And I can, factors of 6 that give me -5 would be -3 and -2, so x minus 2 and x minus 3. So that tells me I actually have vertical asymptotes at x, and I'm going to set x minus 2 for x equals 0. X minus 2 equals 0 would give me an asymptote at x equals 2, and x minus 3 equals 0 would give me an asymptote at x equals 3. And any horizontal asymptotes would be I'm going to look at the coefficients of the first term for the horizontal. And I see that n is less than m, which means that I have a horizontal asymptote at y equals 0. Now this one's going to be kind of an interesting one, because if I were to look at the numerator and the denominator and factor them both out, I would have, if this is a difference of squares, x minus 2, x plus 2 in the numerator, and the denominator is x times x minus 2 times x plus 3. What's going to happen is, at this point right here, that should be a hole in my graph. So I'm going to graph this and see what it really ends up looking like. So I have my horizontal asymptote at y equals 0. I have a vertical asymptote at x equals 0. And I have one at x equals 3. There should actually be a hole at where x equals 2, which it shows me that it's undefined there. And so even though it's not shown there, there's going to be a hole in the graph. So it wasn't an asymptote at all. it was a hole because those canceled out.